Okay, so we are going to finish off the week 8 material in this video, and it's going to be integrating exact one forms. So we've seen how to integrate one forms generally, take a parameterization, take the derivative with the one form that you are integrating, dot the two things together, and then integrate. So sometimes you can spot that a one form is exact, and we know some ways of checking whether that's the case. And when you can do so, it turns out that it's very easy to integrate it, because you just have to write down what the thing was that it is the differential of, and then compute the endpoints of the curve. So that is theorem 2.5.4. So let's write it down. Let omega be the differential of some function f, be an exact one form, and C a curve in AN. The integral of omega over C depends only on the value of f at the endpoints of C. So more explicitly, for a parameterization, gamma, which sends some interval into AN, the integral of your one form over C is just equal to, so let's just write down the notation for that, that is equal to value of f at gamma of b minus the value of f at gamma of a. Right, well, we'll give a quick proof of that, but let me just say something about this. You'll have noticed something like this before. So when you're integrating a function, if you can find an antiderivative, so a function that differentiates back to the one that you're starting with, so this is the normal method of integration that we know and love. You take that function and you simply apply it to the endpoint. So in fact, if your curve is the x-axis, so going from a point x equals a to a point x equals b, then this is precisely saying that that's what you do to get the integral. Okay, so yes, so for that reason, let me just say that. So this is the sort of analogue of the fundamental theorem of calculus, fundamental theorem of calculus for integrals along curves. Okay. So let's give the proof. So we recall that if omega is d of f, so if it's exact, then what we get from df at a point P, so that's a one form, and we apply it to some tangent vector V to get a quantity. This is just the directional derivative of f at P along V. So in particular, df, so we're going to put this, we're going to make this statement just about the curve. So gamma t gives me the point, and gamma dash of t gives me the velocity. So this is the directional derivative of f along gamma. So 1 for every point t. Therefore, if we want to integrate df, which is our one form along C, we would be doing AB of df gamma t gamma dashed of t dt, which we know is just the directional derivative along gamma of f dt, which is equal to d dt of f gamma of t dt. So the equivalence of this and that is just the chain rule. And so that's equal to the integral AB of f of gamma of t by the normal fundamental theorem of calculus, dt, which is equal to just f of gamma of t applied at the point B and the point A, and the difference taken, which is equal to f of gamma of B minus f of gamma of A. Okay, let's have an example just to make sure we haven't gone mad. So if we consider the one form from example 250, we've already seen that it's exact. So so it was f so this was d over f, where f is equal to x squared plus y squared over 2. So d of f in that case was going to be 2x dx, so we're cancelling the 2, so x dx plus y dy. So curve that we used in that example, I believe, was the quadratic. We used the curve y equals x squared with 0 less than x less than 1. And we did compute that the integral along that curve was equal to 1. So let's see if it ends up being the same when we use this this formula. So all we need to do then is to just apply f at the two endpoints of the curve. And remember, even though they're excluded from this range, we are allowed to exclude individual points because that doesn't affect the integral. So, so the theorem says, theorem 2.5.4 says that the integral of the curve df is just equal to f at the point 1, 1. So if we put 1 in there, 1, 1 in there, to get the value f, minus f applied to 0, 0. And that would give us 1 plus 1 over 2 is 1, and then 0 plus 0 over 2 is 0, which is equal to 1. So when you know that, when you can see that something is exact, then you have to do almost no work at all. You do need to work out what the f is, of course. You have to say that it's, if you're going to be able to plug the endpoints in. Right. So that means that you don't have to do any complicated integrals. So you don't have to, no matter what the curve you're given and how complicated the parameterization is, you can very easily just write down the answer. So that's the content of remark 256. It's just that to just say it does not depend on the parameterization, on the parameterization. Well, we knew that anyway, but, or even on the path that curve takes. So you can go from 0 to 1, 1 in any way you like. In that example, you could go by a straight line, or by a parabola, or by anything else, but it will always be the same value. And I said that you would have to compute the f if you wanted to know what the integral was along the curve. Well, there's one example where that is not the case, and that's the corollary I'm just about to write down. So corollary 2.57, if C is a closed curve, so i.e. its beginning and end point are the same, then the integral around the curve is 0. For, be careful, for omega and exact. one form. Proof. Well, it's not going to be too surprising what this is. Suppose omega is equal to df, then theorem 254 tells us that the integral of w around c is just equal to f of gamma of t between the points B and A that define the closed curve, then since gamma of B is equal to gamma of A, so because it starts and ends in the same place, we get that this is equal to f of, let's call this P, f of P minus f of P, and that's equal to 0. Okay, well there'll be lots of opportunity to practice with these things in the next few exercises.